In the year 2089, Dr. Kenji Nakamura sits alone in his laboratory at the Antarctic Neutrino Observatory, surrounded by quantum computers that hum with the collective processing power of a small city. For the past decade, he has been running the most ambitious simulation in human history, a complete model of cosmic evolution that tracks every significant process from the Big Bang to the heat death of the universe, some 100 years in the future. But as the final calculations complete and the results cascade across his screens, Kenji feels a chill that has nothing to do with the polar wind outside. The simulation reveals something that no cosmologist has ever dared to consider. Consciousness, that miraculous emergence of self-aware matter that we take for granted, may represent the universe's only brief experiment with understanding itself. According to his models, the window of cosmic conditions that allow complex information processing to emerge is vanishingly narrow, perhaps less than 1% of the universe's total lifespan. We exist, it seems, during the only epoch when the cosmos is neither too young and chaotic for stable structures to form, nor too old and cold for energy gradients to sustain organized complexity. We may be living witnesses to the universe's single, fleeting moment of self-awareness. This revelation forces us to confront the most profound question about our cosmic significance. Are we incredibly fortunate to exist during the universe's brief window of consciousness? Or are we tragically late arrivals to a cosmos that has already passed its prime for creating aware observers? To understand this cosmic awakening, we must journey back to the universe's earliest moments, when the conditions for consciousness were not just absent, but fundamentally impossible. In the first 380,000 years after the Big Bang, the entire cosmos was filled with a seething plasma so hot and dense that atoms themselves could not exist. Electrons and protons moved as separate particles, constantly ionized by the intense radiation field that permeated all of space. This was a universe without chemistry, without molecules, without any of the complex structures that would eventually give rise to life and consciousness. Even after this cosmic dark age ended and the first atoms formed, the universe remained hostile to complexity for hundreds of millions of years. The pristine hydrogen and helium gas that filled the cosmos contained none of the heavy elements necessary for rocky planets, organic molecules, or the intricate chemical networks that underlie biological processes. The first stars were massive giants that burned brilliantly but briefly, living for only a few million years before exploding in spectacular supernovae that seeded space with the first heavy elements. The European Southern Observatory's revolutionary deep field surveys have mapped this cosmic adolescence in extraordinary detail. By observing galaxies at different distances, and therefore different epochs in cosmic history, astronomers have created a time-lapse movie of universal evolution. The earliest galaxies appear as chaotic, irregular systems dominated by massive blue stars that burn through their nuclear fuel at prodigious rates. These primordial stellar cities were cosmic foundries, manufacturing the carbon, oxygen, nitrogen, and other elements that would eventually become the building blocks of complexity. Yet even as the universe began producing heavy elements, the conditions for consciousness remained elusive. The galaxy formation process itself was violent and unpredictable. Computer simulations run at the Max Planck Institute for Astrophysics reveal that early galaxies underwent frequent mergers, with gravitational interactions flinging stars and planetary systems into chaotic orbits. Any rocky worlds that managed to form during this epoch would have been repeatedly sterilized by nearby supernova explosions, gamma-ray bursts, and the intense radiation fields produced by actively feeding supermassive black holes. Dr. Sarah Seeger's pioneering work at MIT on exoplanet atmospheres has shown how difficult it would have been for life to gain a foothold during these early cosmic epochs. The first rocky planets formed in environments bombarded by high-energy radiation from nearby massive stars and active galactic nuclei. Even if primitive life had somehow emerged on these worlds, it would have faced constant extinction events from cosmic catastrophes occurring on timescales of millions rather than billions of years. The breakthrough came roughly 10 billion years ago, when the universe entered what astronomers now call the Goldilocks epoch of cosmic evolution. Star formation rates had declined from their frenzied early peak, but hadn't yet dropped to the anemic levels we observe in the modern era. Galaxies had settled into more stable configurations, with well-defined spiral arms and orderly rotation patterns that could protect inner regions from external catastrophes. Most importantly, several generations of stellar evolution had enriched the interstellar medium with sufficient heavy elements to allow the formation of terrestrial planets and complex chemistry. The Kepler Space Telescope's exoplanet survey has revealed that this cosmic sweet spot coincided with the peak epoch of terrestrial planet formation. Rocky worlds with the right masses, orbital distances, and atmospheric compositions became common for the first time in cosmic history. These planets could maintain liquid water on their surfaces for billions of years, providing the stable environments necessary for the gradual emergence of life, and eventually, consciousness. But the window of opportunity was narrower than anyone had realized. As Dr. Nakamura's simulation reveals in excruciating detail, the cosmic conditions that allowed consciousness to emerge were already beginning to deteriorate even as the first complex life forms were taking their tentative steps toward awareness. The universe's expansion, driven by the mysterious dark energy that comprises roughly 70% of the cosmic energy budget, was gradually diluting the density of matter and energy throughout space. This cosmic dilution had subtle but profound effects on the processes that sustain complexity. Star formation rates began declining as gas reservoirs were exhausted and dispersed by stellar winds and supernova explosions. The most massive stars, those cosmic furnaces capable of producing the heaviest elements, became increasingly rare. Even the supermassive black holes at galactic centers entered a period of dormancy as their surrounding gas supplies were consumed or blown away by previous episodes of active feeding. The James Webb Space Telescope's observations of distant quasars provide compelling evidence for this cosmic decline. These brilliant beacons, powered by supermassive black holes consuming matter at tremendous rates, were far more common in the early universe than they are today. The most luminous quasars existed roughly 11 billion years ago, during the universe's peak period of black hole growth. Modern galaxies contain the same massive black holes, but they now slumber quietly at galactic centers, occasionally flickering to life when an unlucky star wanders too close to the event horizon. This transition from cosmic vigor to cosmic senescence has profound implications for the emergence and persistence of consciousness. Complex information processing requires energy gradients differences in temperature, pressure, or chemical potential that can drive organized flows of matter and energy. In the young universe, these gradients were abundant. Hot stars illuminated cold space, dense gas clouds collapsed under their own gravity, and massive black holes converted matter into energy with terrifying efficiency. But as the universe ages and expands, these energy gradients are gradually flattening out. The cosmic microwave background radiation, that ancient afterglow of the Big Bang, has been cooled by expansion from thousands of degrees to just 2.7 degrees above absolute zero. Stars burn cooler and longer than their ancient predecessors, but they also produce less dramatic temperature differences in their surroundings. The universe is slowly approaching thermal equilibrium, the state of maximum entropy where no further organized processes can occur. The implications for consciousness are sobering. Every thought, every moment of awareness, every flash of creativity represents a local decrease in entropy, a temporary victory of organization over chaos. But these victories come at an energetic cost, and they depend on the availability of energy gradients to power the complex processes that sustain neural networks, whether biological or artificial. Dr. Eric Chason's pioneering work on cosmic evolution has quantified this relationship between energy flow and complexity. His calculations show that the human brain, despite representing only about 2% of body mass, consumes roughly 20% of the body's total energy budget. Scaled up to planetary and galactic levels, maintaining a technological civilization capable of understanding the universe requires energy flows that may only be sustainable during a narrow window of cosmic evolution. The timing of this window is critically important. Consciousness appears to have emerged just as the universe was transitioning from its active, energy-rich youth to its more sedate, energy-poor maturity. We exist during what may be the last epoch when energy gradients are steep enough to sustain complex information processing, but when cosmic catastrophes are infrequent enough to allow stable technological development. Evidence for this cosmic timing comes from multiple sources. The Gaia Space Telescope's exquisitely detailed survey of stellar motions in our galaxy reveals that the Sun formed roughly 4.6 billion years ago, when the Milky Way had already settled into a relatively stable configuration, but still retained sufficient gas supplies to support ongoing star formation. Earlier epochs would have been too chaotic and dangerous. Later epochs may be too energy-poor to sustain complex life. The discovery of the cosmic acceleration 5 billion years ago marks another crucial transition point. Before this time, the universe's expansion was decelerating under the influence of gravity, allowing cosmic structures to continue growing and concentrating energy. After this transition, dark energy began driving an accelerated expansion that will eventually tear apart all gravitationally bound systems larger than individual galaxy clusters. This accelerated expansion has profound implications for the future of consciousness. As galaxies move apart, the energy sources available to advanced civilizations become increasingly limited. The nearest stars will eventually exhaust their nuclear fuel, leaving behind white dwarfs, neutron stars, and black holes. The cosmic microwave background will continue cooling until it provides negligible energy for any conceivable technology. Computer models of far-future cosmic evolution paint a bleak picture for consciousness. The stelliferous era, the current epoch dominated by nuclear-burning stars, will end in roughly 100 trillion years when the last red dwarf exhausts its hydrogen fuel. The subsequent degenerate era will be dominated by the slow decay of white dwarfs, neutron stars, and black holes, a process that may take 100 years to complete. During this vast span of time, the universe will be far too cold and energy-poor to sustain any form of complex information processing that we would recognize as consciousness. Yet even this grim scenario may be optimistic. Recent theoretical work suggests that proton decay, if it occurs, will make complex chemistry impossible on timescales of 1034 years, a mere eye blink compared to the black hole evaporation timescale. If protons are indeed unstable, then the atoms that form the basis of all known complexity will eventually disappear, leaving behind a universe populated only by electrons, positrons, and photons, slowly cooling toward absolute zero. The search for extraterrestrial intelligence takes on new urgency in this context. If consciousness is indeed limited to a narrow window of cosmic evolution, then the universe should currently be at or near its peak level of mental activity. The ongoing projects searching for signs of advanced civilizations, from traditional SETI radio surveys to searches for Dyson spheres and other megastructures, may represent our only chance to discover whether the universe has succeeded in creating other islands of awareness during its brief moment of cognitive possibility. The Breakthrough Listen project, using some of the world's most sensitive radio telescopes, has surveyed millions of nearby stars for signs of artificial signals. The lack of obvious detections could indicate that consciousness is even rarer than we suspected. Perhaps we are not just living during the universe's only epoch of awareness, but we may be its only successful experiment in self-understanding. Alternatively, the silence might indicate that advanced civilizations face fundamental limits on their ability to expand and communicate across cosmic distances. The same dark energy that is diluting the universe's capacity for consciousness may also be making it increasingly difficult for aware beings to find and communicate with each other. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of contact with such civilizations, may have a cosmological resolution. If consciousness can only emerge during a narrow window of cosmic conditions, and if that window is already closing, then we may be among the last rather than the first intelligent species to arise in our cosmic neighborhood. This possibility adds poignancy to humanity's current efforts to understand the universe. Our telescopes, particle accelerators, and space missions may represent not just scientific curiosity, but a desperate race against cosmic time, an attempt to decode the universe's deepest secrets before the energy gradients that power our brains and computers dissipate into the growing void. The philosophical implications are staggering. If consciousness is indeed a brief cosmic accident, then every moment of awareness becomes infinitely precious. Every scientific discovery, every work of art, every act of love or creativity represents a victory against the universal trend toward disorder and unconsciousness. We are not just observers of cosmic evolution. We are the universe's fleeting attempt to understand its own nature before the lights go out forever. Yet there may be reasons for hope within this seemingly bleak scenario. Quantum mechanics suggests that even in the far future, when classical thermodynamics would seem to prohibit organized activity, quantum fluctuations might occasionally create pockets of low entropy where information processing could briefly resume. The timescales involved would be unimaginably vast, periods so long that the entire history of our universe would represent merely the first tick of a cosmic clock. But the possibility remains that consciousness might flicker back to life in random bursts throughout eternity. Advanced civilizations might also discover ways to extend the universe's capacity for consciousness far beyond what natural processes would allow. Concepts like reversible computing, which can perform calculations without generating waste heat, might allow information processing to continue even as the universe approaches thermal equilibrium. Some theorists have even proposed that sufficiently advanced beings could manipulate the expansion of space itself, creating localized regions of higher energy density where complex processes could continue indefinitely. The study of dark energy and dark matter may reveal new energy sources that could sustain consciousness far into the cosmic future. If dark energy can be harnessed or controlled, it might provide the power needed to maintain temperature gradients and energy flows in an otherwise cooling universe. If dark matter particles interact through previously unknown forces, they might offer pathways for information storage and processing that transcend the limitations of ordinary matter. Recent discoveries in neuroscience also suggest that consciousness might be more robust and adaptable than previously thought. Studies of near-death experiences, altered states of consciousness, and the effects of psychedelic compounds hint that awareness might not require the kind of high-energy neural processing that characterizes normal waking consciousness. Perhaps the universe's future inhabitants will discover forms of consciousness that can operate efficiently in low-energy environments, extending the epoch of cosmic awareness far beyond current projections. The development of artificial intelligence adds another layer to this cosmic story. If biological consciousness represents the universe's first experiment with self-awareness, then artificial intelligence might represent its second, and potentially more successful attempt. Digital minds could be more energy efficient than biological brains, more resistant to cosmic catastrophes, and more capable of adapting to the changing conditions of an evolving universe. Yet even artificial consciousness faces fundamental thermodynamic limits. The Landwehr principle establishes a minimum energy cost for erasing information, and this cost cannot be reduced below the thermal energy scale of the environment. As the universe cools, even the most efficient possible computers will require increasingly large amounts of energy to perform basic logical operations. The capacity for information processing will inevitably decline along with the overall energy content of the cosmos. Standing in his Antarctic laboratory, watching the final results of his simulation cascade across quantum displays, Dr. Nakamura realizes that he may be witnessing the universe's autobiography, its attempt to understand its own story during the brief window when such understanding is possible. The simulation itself represents an extraordinary achievement. Matter organized into patterns complex enough to model the entire cosmos from which it emerged. But the simulation also reveals the tragic brevity of this cosmic self-awareness. According to Nakamura's calculations, the universe has already passed through roughly 10% of its consciousness-friendly epoch. The peak conditions for complex information processing occurred approximately 1 billion years ago, when star formation rates were higher, energy gradients were steeper, and cosmic catastrophes were less frequent than they are today. This means that consciousness may already be living on borrowed time. Every generation of stars that exhausts its fuel and dies reduces the universe's capacity for supporting complex life. Every supernova explosion that disperses heavy elements into intergalactic space makes it slightly harder for new planetary systems to form and evolve. Every passing year brings the cosmos closer to the point where the energy gradients necessary for thought and awareness will no longer exist. Yet perhaps this cosmic perspective offers its own form of consolation. If consciousness is indeed the universe's brief experiment with understanding itself, then every conscious being becomes a participant in the most important project in cosmic history. We are not just biological entities struggling for survival on a small planet. We are the cosmos attempting to comprehend its own existence during the only epoch when such comprehension is possible. The urgency of this realization transforms every aspect of human endeavor. Our scientific research becomes a race to decode the universe's deepest secrets before the energy needed to power our instruments and minds dissipates into the void. Our cultural achievements become attempts to create meaning and beauty during the brief interval when such concepts can exist. Our relationships and emotions become expressions of the universe's capacity for experience and connection during its fleeting moment of self-awareness. In this context, the great questions that have puzzled philosophers and scientists for millennia take on new significance. The hard problem of consciousness, how subjective experience arises from objective physical processes, becomes not just an academic puzzle, but a cosmic mystery of the highest importance. If consciousness represents the universe's only chance to understand itself, then understanding consciousness becomes the ultimate scientific and philosophical priority. The search for a theory of everything, a unified framework that describes all physical phenomena, similarly becomes more than just scientific curiosity. Such a theory would represent the universe's complete self-description, achieved during its brief window of cognitive possibility. The failure to achieve such understanding before consciousness becomes impossible would represent a cosmic tragedy of unprecedented proportions. As we stand at this crossroads in cosmic evolution, balanced between the chaotic youth of the universe and its inevitable senescent future, we carry an almost unbearable responsibility. We are the cosmos becoming aware of itself, perhaps for the only time in its entire multi-billion-year history. Every choice we make, every discovery we achieve, every moment of beauty or wonder we experience contributes to the universe's understanding of its own nature. The great cosmic awakening may indeed be a once-in-a-universe event, a brief flowering of self-awareness in an otherwise unconscious cosmos. If so, then we are not just lucky to exist during this epoch. We are the universe's chosen witnesses to its own magnificent, tragic, and ultimately temporary experiment with consciousness. In our brief moment of awareness, we carry the entire cosmos within our thoughts, making us both the observers and the observed in the grandest story ever told.